Hello, and welcome to part 2 of our video. We have just one gas law left to talk about, and that is what's known as Dalton's law. So Dalton's law deals with what's known as partial pressures. And so this is when we have a mixture of gases. And so it sounds kind of scary, but the idea is actually really simple. We can sort of summarize it in two parts. It essentially states that if we have a mixture of gases, the amount of pressure exerted by each gas is what's known as a partial pressure. And if we sum together the partial pressures of each of the gases, that's going to equal the total pressure of the mixture. So pretty simple. Again, each gas in a mixture has a partial pressure, and this is going to be related to how much of that gas we have. And the sum of these partial pressures will equal the total pressure for the mixture. And so if we look at a really simple example here, if we take 2 atmospheres worth of pressure of helium and 4 atmospheres worth of pressure of argon, and we combine them together, we end up with a new total pressure of 6 atmospheres. But still, 2 of those atmospheres come from helium. That's the partial pressure of the helium. 4 of them come from the argon. And perhaps a better example is shown on the next page here. We're going to take a look at air. So air is, of course, a mixture of gases with which you're familiar. The total pressure of the air is 760 torr, or millimeters of mercury, at sea level. So what we see is in air, 78.2% of the air is going to be nitrogen. And what that means is 78.2% of our 760 millimeters of mercury is going to be the pressure of the nitrogen. So again, if 78.2% of our gas mixture is nitrogen, 78.2% of the pressure will come from the nitrogen, which is where this 594 number comes from. And if 21.0% of our gas mixture is oxygen, that means that 21.0% of our total pressure will be the partial pressure of oxygen. So again, 21.0% of 760 gives us 160. And then finally, we have a mixture of trace gases, including CO2 and water and argon and methane and so on and so forth. That composes about 0.8% of the air, and that means that 0.8% of our pressure is going to come from this gas mix, or about 6 millimeters of mercury. So again, key points here: if we have a mixture of gases, the partial pressure of each gas is directly related to how much of that gas we have. And then additionally, the sum of these partial pressures is going to equal the total pressure. And so another place, and where you might be most interested in the partial pressures, is going to be with blood gases, because this is important in our bodies. So in particular, we have significant amounts of both oxygen and carbon dioxide dissolved in our blood. And so if we look at the oxygenated blood, so the blood that's in our arteries, so leaving our lungs and going out towards our bodies, we have about 100 millimeters of mercury for the partial pressure of oxygen, and about 40 millimeters of mercury is the partial pressure of CO2. Now, once the blood has sort of dropped off its oxygen in the body and it's returning, what we're going to see is we have a much lower pressure of oxygen. So we've gone down from 100 millimeters of mercury to about 40 millimeters of mercury in our venous blood. And then we have 46 millimeters of mercury of CO2. So we have less oxygen and more CO2 than we did before. So the blood gases are going to be different in different parts of our body, essentially how, whether we're sort of leaving the lungs and heading out towards the body, or returning from the body back towards the heart and lungs. And then also these blood gases will vary depending on patient health. That's where you might be interested. So if a patient's cellular function is not working right, or their lungs aren't working right, you might see different values here for their blood gases. So it's an important test, looking at these partial pressures in the blood, that can give you some information about what might be going on with a patient. So congratulations, you made it through. Please end the video and complete questions 7 and 8.